We are going to work through two different problems where we think about the power dissipated by light bulbs in a circuit. In both of our problems, we're going to have three identical light bulbs, but we're going to connect them in the circuit in different ways. What our goal will be is to figure out the power dissipated by each one of those light bulbs and to determine which one of those light bulbs would burn the brightest. Here we have three light bulbs, each with the same resistance, 100 ohms. They're arranged like such. We've got light bulb A, which is in series with light bulb B, and these two are along one branch, which is in parallel with light bulb C. And then this circuit is being supplied with a potential from our battery, and that potential is 120 volts. And we need to figure out which one of these light bulbs burns the brightest. To do that, we have to figure out what is the power dissipated by each one of these bulbs. The greater the power, the more brightly that bulb will burn. The equation for power here, we can write it three different ways. The power dissipated by our light bulb could be the current times the potential. It could be the potential squared over the resistance. It could be the current squared times the resistance. To figure out which one of these bulbs burns the brightest, we are going to figure out the current and potential across each one of these bulbs, and then we can calculate the power dissipated. When we look at our circuit, we see that A and B are in series with each other, but this branch right here is in parallel with this branch right here. When our resistors are in parallel branches, the potential across them is the same. So if I bring in my voltmeter and I measure the potential between here and here, it will be the same as what's supplied by my battery, 120 volts. If I measure the potential between here and here, it will be the same as what's supplied by my battery, 120 volts. So between here and here, we've got 120 volts. That means that light bulb C has a potential that is the same as the potential supplied by my battery. Light bulb C has 120 volts of potential. Okay, now let's think about light bulbs A and B here. Let's think about their potential. Well, they're in series. So when we're in series, the potential has to add up to be the total potential. Now, since these two are in series with each other, but these two are also in parallel with this branch, if this branch got 120 volts, this branch gets 120 volts. So V total is going to equal the potential across bulb A plus the potential across bulb B. Now, they both have the same resistance. If they have the same resistance, that means that both of these bulbs are going to have the same potential across them. That means that both of those bulbs, well, they're along the same branch of the circuit here, so they're both going to be getting the same current as well. So if they both have the same resistance, they're both going to have the same potential across them if they're right here along the same branch. So VA has to be the same as VB. Their resistances are the same. So the total potential has to equal twice any one of their individual potentials. So let's just say it's twice VA. So V total was 120 volts. So 120 volts divided by 2 tells me that the potential across light bulb A must be 120 volts divided by 2 must be 60 volts. So the potential across bulb A is going to be 60 volts. And since bulb A has the same resistance as bulb B, the potential across it must also be 60 volts. Okay? Well, now we can find the current. This is also the same as the potential across B. Now we can find the current through each one of these light bulbs. And the current, well, if Ohm's law, V is equal to IR, we solve it for I the current will equal the potential divided by the resistance. So the current through bulb A must equal the current through bulb B, must equal their potential of either A or B, divided by the resistance of either A or B, because they're the same. So the current running through A and B would be our 60 volts of potential across either A or B, divided by their resistance. Each one of them has an individual resistance of 100 ohms. So the current through both A and B is 0.6 amperes. 0.6 amperes, 0.6 amperes. Okay, and then to find the current through bulb C, we can do the same thing. IC is equal to VC over RC. Okay, and so then that is going to equal, we've got 120 volts of potential across it, divided by the resistance of the bulb is 100 ohms. And then 120 volts divided by 100 ohms gives me 1.2 amperes. So the current through bulb C is twice the current that's going through A and B. Now, to find the power dissipated by all of our bulbs, we could use any one of these relationships here. But we already have the current and we have the potential, so we can just multiply the current times the potential to give us the power dissipated by our bulbs. So the power dissipated by bulb A is going to be 60 volts times 0.6 amperes, so that's 36 watts. And the same for resistor B, because it has the same potential and current, that's 36 watts. And then for bulb C, we've got 120 volts times 1.2 amperes, that's 144 watts of power that's being dissipated by bulb C. So bulb C here is the one that's going to burn the brightest. We see that bulb C actually dissipates 4 times the power of either bulb A or B. So bulb C here is our one that's going to burn the brightest. It's going to dissipate the most power. Here we have our circuit. This time we still have 3 light bulbs, each with a resistance of 100 ohms, but our light bulbs are arranged in a new configuration. And we need to figure out which one of these light bulbs burns the brightest, and we're still being supplied with the potential from a battery of 120 volts. All right, and so I've got my chart here. In order to find the power, we can find the current or the potential or both, and use these relationships right here for power in order to figure out which one of my bulbs burns the brightest here. The attack of approach I'm going to use for this one is a little bit different than the one that we did for the pre-lab. This time I am going to find the total resistance of this circuit, then I'm going to find the total current of this circuit and work backwards. In the pre-lab problem, I did more of a kind of conceptual thinking about our rules for parallel and series, but here I think it makes more sense in order to get the total current in our circuit first. And to do that, we have to find the total resistance of this circuit. So the total resistance of this circuit, well, we've got okay, let's think about the current has to flow through resistor or light bulb A. Then it branches off here at this junction through bulb B or through bulb C. And then it comes back together over here at this junction. All right, so let's find the total resistance or the equivalent resistance for these 2 resistors in parallel first. I'm going to call that resistance for these 2 in parallel RBC. So 1 over RBC, this are using our rules for our resistors in parallel, has to equal 1 over R1, or RB, plus 1 over RC. So the inverse of that, RBC, is equal to 1 over RB plus 1 over RC, all to the minus 1. That's the inverse. So that will equal 1 over 100 ohms plus 1 over 100 ohms, all to to the inverse, raised to the -1, and that gives us a resistance, total resistance for these two in parallel of 50 ohms. Okay? Now, these two resistors in parallel, that combination is in series with our resistor A here. I keep on calling them resistors. They're light bulbs, but light bulbs have some amount of resistance here in this problem, 100 ohms. So these two bulbs in parallel are in series with bulb A. So then the total resistance here of my circuit, our total, will be the resistance of bulb A plus the total resistance of these two bulbs, B and C, in parallel. So that will be 100 ohms plus 50 ohms. That's 150 ohms. So the total resistance of my circuit here, I'm going to put that here, our total, is 150 ohms. And my whole circuit is being supplied with 120 volts of potential. Now I can go ahead and find the total current running through my circuit because I've got the total resistance and I know the total potential. So rearranging Ohm's law for the current, the total current in my circuit is equal to the potential supplied by my battery divided by the total resistance. So that's 120 volts divided by 150 ohms. My total current is then 0.8 amperes. Here we go, 0.8 amperes. I've already got, actually, well, I'll put the unit on here, but I put the unit in my header here for my table so I don't have to repeat those units all the way down if I don't want to. Okay, so how does this help us? Well, that total current is running through my bulb A here. So bulb A is getting this full current of 0.8 amperes. So bulb A has a current of 0.8 amperes. Then that current has to split through bulb B and it has to split through bulb C. Now, I can go ahead and find the potential across bulb A using Ohm's law. So the potential across bulb A is equal to the current through bulb A times its resistance. So that's 0.8 amperes times 100 ohms, and that gives us a potential across bulb A of 80 volts. Okay, so 80 volts across bulb A. Now let's see here. Okay, so 80 volts across bulb A. Okay, now remember bulb A is in series with bulb B and C, which are in parallel. So when we're in series, the total potential has to equal the sum of the potentials across our individual elements. So the total potential supplied by my battery has to equal the potential through bulb A plus the potential across the combination of these two resistors in parallel. I'm going to call that potential BC. Since these two are in parallel, the potential across B is the same as the potential across C. That I could use this in order to find the potential across the equivalent resistor of B and C in combination, which will be the same as the potential across B itself, the same as the potential across C itself. So if I solve this for BC, we could say VBC is equal to the total potential minus the potential across bulb A. So that's 120 volts minus 80 volts. So the potential across my combination of B and C in parallel is equal to 40 volts. And again, since these two are in parallel, they have the same potential across them. When we have resistors in parallel, they have the same potential. So both B and C have a potential of 40 volts. Okay, and now I can use Ohm's law, solve it for the current, in order to get the current through resistor B and the current through resistor C, or bulb B and bulb C. Okay, so they both have the same potential across them, B and C. They both have the same resistance. That means they're both going to have the same current. And let's see, I'm kind of running out of room here. So we can say that the current through resistor B is equal to the potential across resistor B divided by its resistance. So its current will be 40 volts divided by 100 ohms, and that's 0.4 amperes. Okay? And that current is going to be the same as the current through resistor C, because they both have the same potential across them and they both have the same resistance. Now look what happens here. We've got 0.8 amperes of current coming in through bulb A. Bulb B and C have the same resistance. The current has to split, and because B and C have the same resistance, the current splits evenly between these two branches in parallel. So 0.8 amperes separates into 0.4 amperes and 0.4 amperes. So when we're in parallel, the total current has to equal the sum of the current through my individual branches. So 0.8 amperes equals 0.4 amperes plus 0.4 amperes. And now that we've got the current and the potential for each one of my bulbs, I can find the power. And I'll just go ahead and use this relationship. Power is equal to current times potential, since we had to find both of those here. Well, we didn't have to, but we went ahead and did it anyway, so you can see all the different ways that you could approach this problem. You could have stopped with just finding the current and get the power. You could have stopped with just finding the potential to get the power. But all of this stuff fits together kind of like a puzzle, and it's kind of hard to figure out only the current or only the potential. Sometimes you have to get the potential of one of these things in order to get the current of the other thing. So if we find the power by taking I times V, then we get that the power dissipated by bulb A is 80 volts times 0.8 amperes, 64 watts. Okay. And then the power dissipated by B and C will be 0.4 amperes times 40 volts, 16 watts. Okay. So in this problem, we see that bulb A dissipates the most amount of power, so it's going to burn the brightest.